So we can also use displacements to calculate the shear strain and the slope within any point of a rigid body. So again, we're starting off with a undeformed element QBCD, and we're looking at after we apply a stress, we form an element Q prime, B prime, C prime, and D prime. Okay, so from these elements, we can calculate the shear strain. So we know that the shear strain, we defined it earlier in the lecture as being the change in the angle of BQD, right? So we know that it's going to be equal to the angle BQD minus the angle B prime, Q prime, and D prime. All right. So the question is, so we can do angle BQD is just going to be equal to pi over 2 radians. All right, and then the angle B prime, Q prime, D prime is going to be equal to pi over 2 minus the angle alpha, which I'll highlight. All right, and then the angle beta. All right, so minus alpha minus beta. All right, so if we add those all together, what we'll end up getting is we'll just get that the gamma xy will be equal to alpha plus beta. Okay, so how can we calculate those two angles, alpha and beta? Okay, so we can use the triangle. All right, that goes from point Q prime to a point D2, which is just along the x-axis, all right, to the point D prime. All right, so if we use this triangle, it's a right triangle, we can calculate the angle alpha using the sides. Okay, so we know that the tangent of alpha would be equal to d prime over d2, the length of d prime over d2 divided by the length of q prime over d2. So we know that q prime over d2 is going to be approximately equal to delta x, or the length of the element, and we know that the change in this height is going to be equal to just dv dx delta times delta x. So the delta x's will cancel out, and we're left with just dv divided by delta x. So when alpha is really, really small, we can approximate tangent alpha as being equal to just alpha. So we can say that alpha would be equal to dv dx. Right? In a similar fashion, we could use the triangle Q prime, B prime, and B2 to calculate the angle beta. So if we use that triangle, we can say that tangent of beta is going to be approximately equal to beta, because again, beta is going to be a very small angle, and we can say that's going to be equal to B prime over B prime, the length of B prime to B2 divided by the length of Q from Q prime to B2. Right? So if we do that, that should be equal to delta y times d u dy, and we'll end up with just du dy for the angle beta. All right, so if we go back to our original equation, we can say that our gamma xy is going to be equal to alpha plus beta which is just going to be equal to dv dx plus du dy. All right, and then our last value that we might be asked to calculate is if we want to know the slope of any point within our body. So the slope, or which is oftentimes they're referred to as the mean rotation of a part, is known with the letters theta, capital theta, x, y, and then that's going to be equal to the average of the angles. So we'll get it'll be equal to 1/2 minus uh, uh, alpha plus negative beta. Okay, so it's the average of the two angles that the system rotated by. So we end up getting is going to be equal to alpha minus beta over 2. If we plug in the two values that we had, we get 1/2 alpha was equal to dv dx plus the differential, and then beta was equal to the differential of u with respect to y. Right. So that concludes how you can calculate the shear stress or shear strain, gamma xy, and the slope using the shear, the displacements u of xy and v of xy for a component on an engineering component. All right, so we're going to do an example problem that will show how you can calculate the different strains and stress, the different normal strains, shear strains, and the mean rotation of a part with a known displacement field u and v.